Welcome back to part 2 of our Power Electronics Explainer series right here at EWC. Today, we're jumping into a highly practical tutorial-style walkthrough that's focused entirely on extracting circuit efficiency data using QSpice. So we're moving past those basic steady-state calculations today and diving deep into the dynamic steady-state. Because let's be real, this is where the actual challenge of power system design lives. It's during those ultra-fast on and off switching phases that our power devices reveal their true, non-ideal nature.
So I want to start by asking you a question. Where are your hidden power losses? We so often look at a circuit in a steady state, fully on or fully off, and we just calculate our ideal math. In the off state, current is 0, so power is 0. In the on state, voltage drop is basically 0, so power is nearly 0. It all seems perfectly efficient, right? But that completely assumes the switching happens instantly, and it doesn't. There's a finite, incredibly critical time interval where these transitions take place, and during that interval, neither voltage nor current is 0.
This setup perfectly illustrates exactly what we're talking about. We're looking at a simple but really effective QSpice MOSFET switching schematic. Think of me as a mentor just kind of looking over your shoulder as we set this up together. We've got a DC source providing 24 volts, and that's powering the drain of our SiC power MOSFET, specifically a UJ3C065080T3S, running through a 10-ohm resistive load. Our gate is driven by a pulse generator that's kicking out a 10 kHz rectangular wave. The duty cycle gives us a 30 microsecond on time and a 100 microsecond period. Now we've set up a 2 millisecond transient analysis so we can actually observe this repetitive dynamic behavior, but to really understand the efficiency we're getting here, we have to extract the data properly.
To do that, we're going to rely on a few specific QSpice command line directives. We execute these to calculate the exact averages. First up, we use .measPout AVG, and that calculates the time average of the output power delivered to our load. Next is .measpin AVG, which calculates the average power drawn from our 24-volt supply. And finally, we calculate the efficiency parameter directly using .measEffeg param, pout divided by pin times 100. Actually executing these commands and parsing the raw output data is absolutely essential for getting an accurate, real-world picture of our system's true performance.
Now, what's truly fascinating about this macro-level view is what it's hiding from us. Up top, we have our drain voltage, in the middle is our drain current, and down on the bottom is the instantaneous power dissipated in the MOSFET. If we look at this over a 2 millisecond span, it looks perfectly clean, doesn't it? It's a beautifully stable, steady-state operation. The voltage and current waveforms look like these ideal, vertical rectangular blocks. There are no obvious conduction losses, just a couple of tiny blips on the power graph. Well, this is exactly what we call the macro-level illusion. Because here is the undeniable truth. While a standard oscillogram might look completely clean at a macro level, the real engineering is happening down in the microscopic time domains. We cannot trust the illusion of perfectly straight vertical lines. To genuinely understand the dynamic losses in this circuit, we have to shatter this illusion and zoom in hundreds of times to witness the physical reality of what's happening at the very edge of those switching events. 13 nanoseconds. That is the extremely brief window of time we are about to zero in on. Just 13 billionths of a second.
Diving straight into a single switching cycle, we expose the 13 nanosecond MOSFET turn-on transient. See that perfectly vertical line from the macro view? It's actually a gradual slope. As the gate capacitance charges, the drain voltage drastically drops and the drain current drastically increases. During this tiny 13 nanosecond window, the voltage and current overlap. They're both present at really high values simultaneously, and that overlap generates a massive power spike reaching over 14 watts on the dissipation curve. The device is physically passing through its linear region, dissipating a massive amount of energy as raw heat before it finally settles into its on state.
So the takeaway here is that simply turning the MOSFET on creates a massive power penalty. But let's look a little further down the timeline. What happens during the turn-off phase, when the MOSFET actually tries to stop the flow of electrons, but the current just cannot instantly cancel out? Well, we slam right into a transition that takes 25 nanoseconds. Here is that 25 nanosecond turn-off transient. The device is trying to move from the on state back to the off state. The drain current drops, sure, but it doesn't instantly drop to 0, and at the same time the drain voltage is rising rapidly. So once again, we've got this time window where both voltage and current coexist at significant levels, and that resulting red power dissipation curve reveals another huge sustained power spike. You have to remember, these spikes are not anomalies. They're the inevitable physical reality of non-ideal power devices crossing through their linear regions. And that brings us to a really critical concept, dynamic circuit efficiency. Basically, this is an efficiency calculation that actually integrates the energy lost during these exact microscopic switching transients over time. It's essentially calculating the geometrical area of those red voltage current power spike triangles we just looked at, multiplying it by the switching frequency and adding it to your baseline conduction losses. If you aren't accounting for dynamic efficiency, your thermal management calculations are going to be wildly inaccurate. Pulling back out to our macro view, let's check the final tally. Using those QSPICE.measure directives we established earlier, the software has integrated all those 13 nanosecond and 25 nanosecond power spikes across our entire simulation. The final calculated efficiency gives us a result of 99.1806%. If you look really closely at this graph, you can actually spot the slight difference between the green line, the power generated by the source, and the orange line, the power dissipated by the load. That tiny little gap represents the power lost purely during switching. Now, nearly 99.2% sounds pretty great, but keep in mind, this simulation hasn't even factored in parasitic inductances, distributed capacitances, or non-ideal PCB traces yet. And honestly, this is exactly why parsing this raw output data is so essential for modern design. We're looking at frequency-dependent dynamic losses here, because those 14-watt power spikes happen every single time the MOSFET turns on and off. The faster you switch, the more spikes you get per second. As you can see, as the switching frequency increases along the x-axis, the overall efficiency on the y-axis steadily and non-linearly decreases. Pushing for higher switching frequencies so you can shrink your passive components means you are inevitably going to incur higher dynamic losses and a lot more thermal stress.
The ability to actually observe these microscopic events in real time, integrate that switching energy, and compare parameters before a single PCB is ever fabricated, that's what separates a functioning prototype from a commercial failure. The dynamic regime is the true benchmark for power electronics design today. So I'll leave you with this. How much parasitic power is silently burning away in the microscopic shadows of your current design? I really hope this deep dive into QSPICE data extraction has equipped you to go find out. Compute before building with Engineering World Company.